I'm in a hotel room and I'm about to step into a lift, and I'm interested in how smooth the journey is. And to tell me how smooth it is, I'm going to take this bottle of water in, and I'm going to look at the surface of the water when the lift starts off, when it's descending, and when it comes to a halt, and we can see how smooth the journey was by looking at the surface of this water. Descending, can't even sense it. Water perfectly still. I'm now descending, about to come to a stop. You won't get a smoother journey than that. So how do the engineers manage to produce such a smooth ride on a lift? When we got on the lift, there was no sensation of the lift falling away from our feet. That was noticeable. And there was no sensation of the lift pushing against our feet as it brought us to rest. There was no sensation of the lift accelerating as it reached a top speed, and there was no sensation of the lift decelerating. It was all done very, very smoothly. How did it do that? Well, it's relatively simple physics. It's relatively simple physics. Now this is a force issue, because clearly the machinery is pushing and pulling on the lift. This is a force issue. And in this particular text, it's best to use speed time graphs. Now the journey took 12 seconds, and the height was approximately 12 metres. So the average speed of the lift was 1 metre per second. It was 1 metre per second, that was the average velocity. Best to use the word velocity here. Velocity is a vector. Now, so if I had to draw a speed time graph of that, the first obvious thing to do would be to draw this graph here. But this graph is impossible, because it's suggesting we're going from 0 metre per second to 1 metre per second and no time at all. Even if the time was a 50th of a second, say, that would be a very rapid acceleration. And since this lift can be 2 to 3,000 kilograms, that would require a very, very large force. And I'm not really sure if the machinery could cope with that. It would certainly be uncomfortable, and it would probably break the lift. That graph is not a graph that the velocity of the lift follows. So suppose we choose a gentler acceleration then, 1 metre per second. Would that work? Well, it's a wee bit better, but you've got these corners on your hands of this graph, and these corners represent abrupt changes, and the abrupt changes would feel uncomfortable, and again it could damage the lift mechanism. So it's best not to have a graph like this. No, we want to smooth out these corners. As you can see, now you've got the lift gradually rising to the constant acceleration, and gradually rising to the constant velocity, and gradually rising to the deceleration, and gently coming to rest at the end. That's what that graph does. Now the question is, what is interesting now though, is how we achieve these curves for our lift. How we achieve these gradually changing curves for our lift. Now, to achieve it, the engineers have to be well aware of what's meant by the jerk. Now, what is a jerk? Because it's controlling the jerk that allows us to put these four curves on our graph. How do we do that then? So what do we mean by jerk then? Well, if a body experiences an unbalanced force, that body will accelerate for the duration of that unbalanced force. But however, if the unbalanced force is changing, suppose it's increasing, if the unbalanced force is increasing, then the acceleration of that body will also increase. And the rate of change of that acceleration divided by time, is called the jerk. and it's got units of meters per second per second per second, or ms to the minus 2 divided by seconds, or ms to the minus 3. That's the units of jerk, the rate of change of acceleration. Now, interestingly though, if the unbalanced force acting on the body is increasing at a constant rate, the acceleration will also increase at a constant rate, and the velocity time graph of the body that's experiencing that changing unbalanced force will be a perfect parabola, as we shall see. So suppose then the lift is at rest on the lower floor and is about to rise, and we want the velocity to be a parabola in the beginning. How do we achieve that? Well, let's look at its displacement first of all. Its displacement must be of the form some constant times t cubed, where the constant has to have units of jerk ms to the minus 3, because ms to the minus 3 times second cubed give you units of meters, which is what we need. If we differentiate the displacement with respect to time, we get its velocity. So if we differentiate t cubed, we get 3t squared. 3t squared is the velocity. That's a quadratic, meaning when you plot that curve, you get a parabola, which is what we want. A nice smoothly rising velocity. If we differentiate the velocity, again we get an acceleration, d2s by dt squared. It's an acceleration. So when we differentiate 3t squared, we get 6t. 6t is a straight line, a straight diagonal line to the origin, and that's the acceleration, meaning the acceleration is a function of time. So as soon as you press the lift, your acceleration doesn't go up to immediately 1 meters per second. No, it gradually rises to that. So a hundredth of a second after 1/100th of a second after you press the button, your acceleration isn't going to be some arbitrary number, but it's going to be 6 times 100th, and that will be your acceleration. So it was quite a low acceleration with a low displacement and a low velocity. This is why you hardly hear it. This is why you hardly feel it. If you differentiate 6t, you get d3s by dt cubed, and that's equal to 6, and that's the jerk in this particular case. So s is equal to 1t squared gives you a jerk of 6. So s is equal to 1/6 of t cubed will give you a jerk of 1. Now this should remind you of another expression, s is equal to 1/2 at squared. Now, if you choose acceleration to be equal to 2, then you've got s is equal to t squared. And that will give you a straight line for the velocity. It will give you a parabola for the displacement, and it will give you a straight horizontal line for the acceleration. And that's not what we want, as we've discussed earlier. So I've got these two graphs for you, so you can compare. S is equal to t squared and s is equal to t cubed. And we'll find, and you should find, if you compare the both, it's the s equals t cubed graph that we need to have for our constant jerk. Then this is followed by a short video that shows you how the three graphs are generated and how the force on the lift changes as it goes through the first jerk.
Dig it! Can you